In this video, we're going to introduce the concept of a geometric sequence, okay? As opposed to an arithmetic sequence. We saw in previous videos that arithmetic sequences are these sequences that, say, for example, I'm just making this up here, that are advancing or increasing or decreasing by a constant difference every time. We say this like constant difference allows us to basically forecast or predict what values would be in the future. So predictable sequences like this, another predictable sequence is a geometric sequence, okay? And we say any sequence that is geometric, we say it has to have a common ratio. Okay, so basically we say if the ratios of consecutive terms are the same, then it is geometric. So the sequence a1 through an and onward, we say is geometric if there exists a number r. We're going to call this number r the common ratio. So we say the common ratio is r. Okay. What I'm going to tell you is this common ratio serves much the same purpose as D did when we talked about arithmetic sequences, okay? But we say what R is essentially this ratio between terms, consecutive terms that is. So remember, we say consecutive terms, we say if this is the nth term, then we'll divide it by the term right before it. So we would say A2 divided by A1, or A3 divided by A2, or A4 over A3. It's really important that we can express this as a fraction, as a matter of fact, but this would always be some common number, okay? We're going to refer to this as the common ratio. So for instance, down here, what we're going to do is we're going to determine all these sequences right here, are they geometric, say? And if so, what we want to do is identify the common ratio, okay? So to check for this, what we're going to do is this. We're going to take out two terms. We're going to talk about what geometric sequences really are doing here with this common ratio and then relate it to arithmetic. But we say, if we took two terms here, we say like A2 divided by A1. In this case, we'd say our second term is 4 and our first term is 2. We say we get 2. And so we're calling this R. I'm going to put a box around this. As a matter of fact, if we did A3 divided by A2, I'm going to do a couple more here. We say is 8 over 4. So I get 2. This is the common ratio again. And last but not least, if we said like 16 divided by 18, of course, you say, 16 divided by 8, we get 2, and this is R again. So here's the deal. What we look at when we talk about geometric sequences are sequences that are not adding or subtracting the same constant every time, but have a common what we call ratio. So we call it a common ratio because we have to be able to like divide a term by the term before it to find it. So we say this is our 2 that we found on this R right here. This is exactly the 2 you're finding. It just says you're multiplying by 2 every time. But that's what geometric sequences do. They just multiply by the same number every time. So you notice here I give the first term, second term, third, fourth, all the way up to A4 here. We got A3. A1's very important. But we say that this term right here, this is very important as well. This is the nth term of the sequence. So we say the nth term, we usually write it this way. We say there's some sequence an where an is equal to 2 to the nth power. What I want to point out here is this. This is the same thing as 1 times 2 to the nth power. So this is kind of like, if we're talking about a function notation here, we're talking about something that would look like this. Y equals, and then we'd have, I'm saying 1 times 2 to the n. We would have something that looks like this, a times b to the x. And I know I've seen something like this before. It is purely exponential. Okay, so we say we have some base, some initial value right here. We start with 1, and then we're growing by a factor of 2 every time. We're doubling every time that n goes up by 1. Okay, so long story short, what we need to know is this. We say the rule. I guess we'll get into the rule for geometric sequences in the next video. But for right now, what I want to do is this. I want to find the common ratio if it exists. So is there a common ratio here? We say, well, I don't know. Is there a number I could take times 12 to get 36? Of course, we would express this as, yes, 36 12s is this number. But this is equal to 3 in this case. So what we've done here is we've tripled this. And again, we say 108. We took 108 divided by 36. Sorry for the proximity there. We say this is our R here. And we get 3 again. So we keep seeing that we get this common ratio of 3. But what this is basically indicating is that every time this is going up by 3. So we say here's our nth term here. We say an. I'll write it that way. But our nth term, this is really interesting. Again, we say that this y equals 4 times 3 to the x power. This should be something like that if it were a function. But we have a rule in terms of a sequence. But the thing I want to point out here is this is a geometric sequence because it's exponential. It's going up by a factor of 3 every time. This is our rate of growth, okay, or common ratio. And then we say that this is our initial value, which we could look at, we would have a 4 but before this here. This is technically the 0th term, so we don't have to worry about putting the 4 here. But you can see how if I divide it by 3, go back when I'd start at 4, okay? So now here's where it gets a little bit trickier. We just need to do some math on these. We say, well, are there a common ratio that exists on both of these? So we say 1/9. I'm going to write it this way. Divided by negative 1/3 is the same thing as 1/9 times the reciprocal. Okay, you multiply by the reciprocal. So here we get negative 1 or 3. We get negative 1/3. So we think this is r, equal to r, question mark. So let's take this. We say negative 1/27. We're going to divide this by 1/9, which is really multiplied by the reciprocal. I get this here, and I see that these cross reduce. And I see that, actually, sorry about that. That becomes a 1. This becomes a 3. So multiplying straight across, I get a negative 1/3 again. So I think that our common ratio here is negative 1/3. You could see that if I keep multiplying by this negative 1/3 every time, by the way, you could see how our terms are going back and forth between positive and negative and positive and negative. And we say, well, then my rule for the nth term is this guy right here. Okay, so last but not least, we'll look at this rule right here. And honestly, I look at this, I say, this looks like a quadratic thing to begin with. It's like a parabola. So this is not multiplying by the same number every time, but we just need to prove this. So we say, well, 4 divided by 1 is common ratio of 4. I don't know. I mean, like, is this r? So we'd say, well, let's take 9 divided by 4. And 9 divided by 4 in this case is like 2.25, just to give you a decimal. But we say equal to r. Well, these are not the same values here. So we say, first of all, this is not geometric because we're not multiplying by the same amount every time. Okay, and the last thing I want to mention before we kind of move into the next video is this, but if these are so exponential, we're talking about this exponential kind of look to these things, you notice that your r value too, when you look at the rule, okay, or we had 3 here, or down here we had negative 1/3. When you look at the rule, we're saying it's always this y equals like a times the base times the, to the x if you were talking about a function. But we'd say that our r value here, our common ratio, is always the base of the exponent, which is kind of an important thing to notice here. Like the rule here was 2 to the n. That was the base of the exponent was 2, so our r value is 2. And down here we say the base of this exponent here is negative 1/3, and that's our r value. Cheers.